Hi everyone, this video will serve as a review for our Newton's Laws and Forces test. I'm going to touch on the most frequently missed concepts behind some of the questions that many of us unfortunately missed the score for a couple of the multiple choice, as well as one of the short answer questions was frequently mistaken. So one of those questions, you can pull up your own Google form that was the multiple choice. There was one question in particular that less than half of us were able to successfully choose, dealing with inertia. The question was simply which animal has the greatest inertia, and then I listed some animals with different masses and different velocities. So I'd like to review the concept of inertia, which is also Newton's first law. Inertia is really, in one word, mass. Inertia is the tendency for an object to maintain its current state of motion, whatever that state of motion is, whether it's at rest or it's moving at some velocity. That is not important when it comes to the idea of inertia. Inertia is how much the object wants to maintain its current motion, and how much it wants to maintain its motion is only dependent on its mass. You can even connect this idea with Newton's second law that says a force will cause a mass to accelerate, but how much it will accelerate depends on the mass and the force applied. So in the list of options in that question, I had different animals with different masses moving at different velocities, but the velocity was of no consequence. Mass is the only determinant of inertia. Another question that was unfortunately missed quite frequently was the same question I gave you on the kinematics test. It dealt with a projectile being thrown, and the question I asked was, which direction is the force acting on the projectile when it's at the apex of its parabolic pathway? Well, this picture you see on screen is a representation of the velocity and the velocity components of a projectile. For example, at the very beginning when it's launched, the resultant velocity, or the actual velocity, is at this diagonal. But to solve anything mathematically, we would split that apart into a vertical and horizontal component. Well, that's just it. All these arrows are representing velocity. They do not tell us what's going on with force. And that's because force is telling us about acceleration combined with mass, but the direction of force is only represented by the acceleration of the object. This picture does not show us anything about that. When we are dealing with a projectile, the one and only force acting on it is gravity, and gravity only acts with its acceleration in the downward direction. And for a projectile, that particular value of acceleration is 9.81 meters per second squared in the downward direction. So no matter where we're talking about in this parabolic pathway, our force and also our acceleration is only acting downward everywhere along. I think many of you were thinking about velocity with that question rather than acceleration or force. Yeah, another question on the multiple choice that was frequently missed involved a person in a gym trying to pick up a dumbbell. But I specifically designed the problem such that the lifting force was not enough to actually lift the object off the ground. Remember, if you want to lift something, the normal force is not going to help you do that. You have to apply a force at least as strong as gravity in order to lift something off the ground to effectively oppose gravity with a fraction more of a Newton than it is pulling down with. Well, if you're only pulling up with some amount of force that is less than the object's own weight, in other words, less than its own gravity, then it will stay there. It will remain at rest on the ground. But the force system is still changing. By you applying your force upward, you are altering the normal force that the floor will still provide upward on that object. And you can see some equations here that detail that scenario. If we're lifting with not enough force to cause motion, then your net force is still zero on an object, but we now have two forces acting upward and only one force acting downward. Therefore, the combination of the two upward forces, in this case, your force applied and your force normal, will equal your force gravity. And so with the values of our dumbbell question, we could have solved for the force normal that I believe was the question I asked. There is one last problem that I would like to go over with everyone, and that is from the free response. In fact, it was the final question on the free response, the one with the sled. The most common error I saw was a lot of us were so focused on the inclines that even when you dealt with a force that was not necessarily acting on an incline, you still applied the incline vector component equations. What I mean is you took your force that was to be broken up into components and applied equations like mg sine theta, mg cosine theta. Those component equations only work for gravity on an incline, not for any force whatsoever. And so I think, again, you kind of replaced your vector component equations with a specific scenario with an incline rather than sticking to the general setup that we've done all the way since kinematics. In fact, let me bring you back to the quick picture of the review page that we took a look at before we took that test. When we have any vector, let's say it's a force vector, and you want to split that apart into components, you're going to effectively multiply the real vector by a trigonometric function with an angle. So if here's our resultant, this diagonal force, and we want to solve for the horizontal component, fx, then we take the full vector and multiply it by a trig function times the angle. Which trig function? Well, the angle here is adjacent to the x. Cosine deals with the adjacent. And so my equation will be f cosine theta for this horizontal component. And then for the vertical component, vertical is opposite this angle, so the sine multiplier will be applied. Many of you either confuse these two trig functions when it comes to the question with the sled, because again, you were thinking inclines, where it turns out that the angle is adjacent to the vertical component rather than horizontal. So sine and cosine switch, and the force can be modified to m times g. But again, that's only true with the gravity force on an incline, not to any force whatsoever that's acting on an angle. So if we go back to that sled problem, the diagram for that problem would have looked something like this. We have an applied force, which we are splitting up into a vertical and horizontal component. Normal force is acting up, gravity force acts down, friction force acts to oppose the horizontal component of the applied force. And in this question, I was asking you to solve for the coefficient of friction acting against the motion of the sled, given that it was moving at constant velocity. Well, let's put everything together here. If the sled's moving at constant velocity, that means that this horizontal component of the applied force is equal to the friction force. So that's what I said over here. However, you can't solve for anything unless you deal with the vertical net force as well, because for friction, you need the normal force and the coefficient of friction. And then for applied force, you need to solve for the proper equation for that component, which is, again, force times cosine of the angle, since the angle I gave you was adjacent to the x component, as is the standard. So let's go over to the vertical components. I'll move my face here so you can see. Up and down, again, no net force. There's no acceleration up or down. And so our normal force plus the vertical component of our applied force will be equal to gravity in this case. The way I wrote that was the normal force in this case will be equal to the difference between applied y and gravity. You could have written that the way I spoke out loud, where F gravity equals Fn plus Fay, but you come to this equation in the end anyway, with adding or subtracting from different sides of that setup. All in all, you step by step would first probably want to solve for your two components of the applied force, because I did give you the amount of applied force on the angle. You then properly apply those components into the vertical and horizontal equations respectively to solve for mu. I hope that this video was enough to make you realize your errors. Hopefully you now see and will not make the same mistakes since everything's laid out for you here. Feel free to rewatch if you need to. I hope you enjoy your vacation, and I will see you when we return for the new year. Take care.